So, can you hear me? Okay. So, we'll start the class. So, so before solving this question, we'll be discussing about vein shear test first because it is involving in vein shear. If let me read out the question. A field vein shear testing instrument. So this total is the instrument shown alongside in the figure was inserted completely into a deposit of soft saturated silty clay with the vein rod vertical, okay, such that the top of the blades were 500 mm below the ground surface. Okay, upon the application of a rapidly increasing torque about the vein rod, the soil was found to fail when the torque reached 4.6 Newton meter. Assuming mobilization of undrained shear strength on all failure surfaces to be uniform and the resistance mobilized on the surface of the vein rod to be negligible, what would be the peak undrained shear strength rounded off to the nearest integer value of kPa in terms of kPa of the soil? So basically, uh, what the question is saying that, uh, okay, first let us discuss what is vein shear test. Then you will understand. So how does it look? We'll discuss that. Okay. This can be done in laboratory, either laboratory or field. It can be done in both ways. So this is to find out the undrained shear strength of the soil. Okay, undrained shear strength of soil. This is to be this is used to find out that. So coming to the lab, so we can take soil sample in a small container, okay, in a small container, then we can do the test. But whereas in the field, it can be done on the ground surface, okay, ground surface, or else if you want to go for a borehole, suppose there is a borehole, there is a hole in the soil. So at the bottom of the borehole, at this place, also this vein shear test can be done. So what is vein shear? How does it look? See, it has a steel rod in between. Okay, a vertical steel rod has four blades around it, which are 90 degrees apart from each other. Okay, so like this. Sorry. So like this, there will be four blades. So each one is separated by 90 degrees. Now you can rotate, you can twist this rod. So as these are blades, or you can say it as veins. Okay, these are veins. As these veins are rigidly connected to this steel rod, when you apply twist to this steel rod, this these are also this will also rotate. Okay, this will rotate. So these are sharp blades. Now these sharp blades, I'll just draw. Uh, so this is a small vein shear, you can say. So you can insert this in any soft clay, right? You take any soft clay, you can insert this, and after inserting, suppose either it can be, just a minute, either it can look like this. This is a steel rod, so it can be inserted only partial amount of the blade length. See, this is, if this is the blade, this is the blade length. Okay, this is the blade length. Now diameter of the vein, suppose if you see in the front view, if you keep two blades parallel to the board, so like this, there is a rod, there is a rod in between. So two, another two blades are perpendicular to this plane, this board, this plane. Now this is the length and this is the diameter, one end, from one end to another end. So now if it is the total height is not inserted, partial length of the blade is inserted to the soil. So that can be one type of test. Another kind of test is fully inserted. You can say, suppose blade like this. Okay, it is fully inserted. If this is the ground level, so what is the difference between these two kinds of tests? See, when it is inserted partial amount of the blade height, then we will apply this twist to the rod so that these all blades will move in this direction. So after insertion, what happens? After insertion, the clay, it is just passing through the clay. Blade thickness is very minimal. So there will be soil in between this, right? Suppose there is a soil. This completely it is filled by soil. Okay, this portion. Okay. Now when you are rotating this, it will try to rotate these soil wedges which are there in between the blades. So this soil wedge which are in between these blades, they will also rotate along with the blades. Now, when they have to rotate along with the blades, that clay has to be separated from the surrounding clay. Surrounding clay means this is surrounding clay. That will not rotate because that is nowhere uh, applied by any load. Whereas this clay is uh, plugged in between these two blades. That is the reason why this clay or this clay. So in between these two blades, this clay will rotate. When this plug, the soil plug, which is in between, which is packed, sandwiched in between these two, when it is rotating, it has to cross the strength between the soil along against this strength. So this is the surrounding soil and this is the soil which is in between these two blades, right? This soil has to rotate along with these blades. When it is rotating, it has to overcome the strength between the surrounding soil, right? Then because of this twist, this total four soil wedges will rotate along with the blades against the shear strength which is there in between the surrounding soil. Okay, so the shear strength is the strength to be overcome is nothing but between soil only. This is also soil, this is also soil, is in between soil, in between soil particles only. Okay, this is one thing, like that. Here the total height of the blade is involved, whereas in this there is not total height is involved. That means soil will be only up to here, soil height will be only up to here. It is, suppose if this is h, okay, then this is less than h, the soil height, the soil width, that is less than h. Okay, like that. So now the test is done. Once you insert, you will apply twist. Okay, and after applying twist, this is nothing but it is calculated in terms of torque, newton meter, okay, or else kilonewton meter. So you are applying twist. When you are applying twist, slowly you will increase the twist 60 degrees per minute. The rod will rotate in this manner 60 degrees per minute. That means how many degrees per second? 0.1 degree, is it? 6 degrees for 60 seconds, then 1 second, right? How many degrees? 1 by 60 into 6, so zero point 0.1, right? Okay, so zero point 0.1 degree per second, the rod will be rotated like that. So when it is rotating like that, the torque value, the resisting torque value will increase, slowly will increase. At one point, the soil will fail. So when that fails, the reading in the dial gauge, suppose this is the dial gauge, okay, so this is the needle which is showing the torque, okay, suppose these are the readings. Dial gauge, this needle, it will the torque will as the torque is increasing, the dial gauge is showing increased torque. When the soil fails, suddenly it starts moving in this direction, in the reverse direction. So that point you have to remember by eye, and you just have to note down that value. That is the torque at failure. Torque at the rate failure. You will note down that torque. So after noting down, by using that torque, the T at failure, you will find out the undrained undrained cohesion. Okay, you will find out the undrained cohesion, that is Cu. Undrained shear strength is also nothing but undrained cohesion only, because Su is what? C plus sigma tan phi, right? S. This is shear strength, this is cohesion, this is friction angle. For the undrained shear cohesion or undrained shear strength, generally only exists for clays, not for sand. When it is for clays, undrained is generally for clays. For clays, this pi value, phi value is 0. If it is 0, automatically undrained shear strength Su will become Cu. So undrained cohesion is nothing but undrained shear strength. You can find out this undrained cohesion using the torque at failure in the vane shear test. So now I hope you understood this. So I'll go to next slide where I will just give you the formula. How do we use the torque to find out the cohesion or shear strength? Okay. Now here in there is a derivation for this in any standard book, as I have been mentioning that Aurora textbook or Gopal Ranjan textbook, you can go through the derivation, but I'll give you a brief idea about the derivation. Okay, see here, when the blade sorry, when the blade is there, when it is rotating, when it is rotating like this, the soil in between these blades has to overcome this, the strength against the surrounding soil, as well as not along this surface, not along this surface, this arc surface, also along the, suppose there is a soil exists above this vein shear, about the top of the blade, above it, suppose this is the ground level, above also there is soil and below also there is soil. The soil has to, this top portion, this top surface has to overcome the shear strength between the above soil above it and this, in between this top surface, that means top and bottom surface. So there will be two areas, one is side curved surface, this one along this, another one is top and or bottom. Okay, top and or bottom. Why and or? If it is inserted fully, then top and bottom both will involve. If it is inserted only half, just like this, suppose this is the ground level, only bottom will involve, top will not involve, because soil is up to here and it is nowhere in touch with the soil above it. It is the top surface. So in that case only top. Sorry, in that case only bottom. So that's how it is, top and or bottom. So if you say this, the torque against which it is rotating, the that is the contributing torque from the side surface is T1, another is T2, the top and bottom. You can say it has to, uh, it has to overcome the two torque values. One is side surface, one is total torque will be T. Let us say. Okay. So now, by using the concept, you can derive what is the T1 value, what is the T2 means in terms of some conventional formulas, the area which is involving, the length, the surface area, and if you go to the top and bottom surface, so from the center point to the, like this circle I'm talking about, if you see from the top, so if this is the circle, this is T2. Okay, if you take a strip, any strip, okay, taking that is dr, whereas this is r, like that, taking all these things by doing integration, you will be getting these two torque values, summing up them. If you mention that as t, which you directly calculate in the laboratory or the field in the dial gauge, okay, wherever it is failing, that is the total torque. But I am, why I am doing this division and why I am writing, because this involves shear strength. Okay, so at the end I want shear strength to be on the left side of the equation, so that I will find out by using this total T. Okay, this total T which I will get from the dial gauge. So that is the reason why I am doing this derivation. So that derivation is available in any textbook. Okay, so let us just, after deriving, you will be getting the equation as T equal to phi into shear strength into diameter. I told you this is diameter and this is length. Diameter into height by 2 plus d cube by 6. So if you make shear strength or left side, then you will get T by pi d square h by 2 plus d cube by 6, right? So this is the formula when vein shear is fully inserted into the soil. That means top and bottom. top and bottom faces are involved. Okay. So in the case of only partial height, okay, only partial height of the blade is inserted and remaining is to the above the ground level. Then the formula will be modified as T by pi into d square inserted length, not to the not full height of the blade, inserted length which is h1. Suppose I can say that here this portion is h1, whereas this total is h, right? Total is total height is h. This is the h, not up to the ground level. Okay, now this is h d square h1 by 2 plus d cube by 12. These two are the formulas to find. This is partial insertion of the blade or veins. Okay, so now going back to the question, let me just, what I'll do, I'll just take this question to the bottom. Yeah, so what is it said? A field vein shear testing instrument was inserted completely. So the vein shear instrument is completely inserted into the soil soft saturated clay, silty clay. Okay, but it is regarded as clay only because we are talking about only undrained shear strength. Okay, with the vein rod vertical. So vein rod is vertical such that the top of the blades were 500 mm below the ground surface. Suppose this is ground surface, so this is 500. That means total top and bottom of the blades are also involved. You have to take the formula, this formula. This formula is used in this case. Okay. Now, upon the application of the rapidly increasing torque about the vein rod, the soil was found to fail when the torque reached. This is a torque at failure. So torque at failure T equal to 4.6 Newton meter or 4.6 10 to the power of minus 3 kilonewton meter, right? That is given. Next, assuming mobilization of undrained shear strength on all failure surfaces, means the side surfaces and also top and bottom and every surface to be, the undrained shear strength is uniform, means it is not varying, linearly varying. Shear strength is less here, shear strength is more here. It's not like that. It is uniform. So no need to be confused. These formulas are for uniform shear strength only. Okay, these are for uniform shear strength, assuming the shear strength is uniform over the blade length. Over the blade length, it is only everywhere it is SU. Okay, and the resistance mobilized on the surface of the rod. That means, see, the rod which is there here. Okay, around this, that shear strength or shear stress is negligible. The shear strength is taken only above and below the top surface, so above the top surface, below the bottom surface, around the surface, side surface, not around the rod. That is what negligible it is said. What would be the peak undrained shear strength? That means undrained shear strength of the soil. So we have the formula, that is T by pi d square h by 2 d cube by 6. Okay, let me write the formula again. Su equal to T by pi into d square h by 2 plus d cube by 6. So here T equal to 4.6 10 to the power of minus kilonewton meter, and D is how much? D is 50 mm, 50 mm, that means 0.05 meter, and H is 100 mm, that means H is 100 mm, that means 0.1 meter. Okay, now you just have to substitute all the values. 4.6 10 to the power of minus 3 divided by pi into t square, 0.05 square h, zero point 1 divided by 2, 0.05 cube by 6. Can one of you tell me the answer? It is in kPa because I am taking it as in terms of kilonewton meter. Okay, here it is in meter square. Okay, meter square or meter cube, meter cube. So finally you will get in kilonewton per meter square or kp. So what is the value? Can you calculate and tell me? I'm expecting answer from one of you. That's why I'm waiting. 10.045 kPa, right? So let us go back to the question again. Nearest integer is what? Nearest integer is 10 kPa, right? So 5, 10, 15, 20. So answer is B. Okay, answer is B, 10 kPa. So we are done with this question. Is there any doubt in this question or in the concept of Wien shear? Can I move to next question? You can write in the chat box also. Okay. So this is the linked data questions. You can say this question is from 2010 gate paper. Um Question number 54 and 55. Okay, each one is 2 marks, but very easy to be honest. Uh, the unconfined compressive strength of a saturated clay sample is 54. Okay, and what is the value of cohesion for the clay? It is asked. And another question is, if a square footing of size 4 meter by 4 meter is resting on a surface of the deposit of above clay, this clay, the ultimate bearing capacity of the footing is how much? So it's very easy. Yeah. How? Can you tell me? Yeah, yeah. Correct. So yeah, in the second case, yeah. Okay. How much? Is there any answer? Yeah, let me come back. Okay. So here, unconfined compressive strength. So unconfined means what? Suppose in the triaxial test, you might have heard the test name triaxial. Okay. So in triaxial, what will happen? There will be a cylinder. Okay. Uh, Acrylic cylinder in which there is a soil sample which is also in the shape of cylinder. So around which water will be there. Okay. Around which water will be there. So there will be a rod which is attached to the top of the soil sample. Okay, it is resting upon one thing, so everywhere water will be there. So water will act on this. The pressure which is coming from the water all around is called confining pressure. Okay, or all round pressure. this called the water pressure which is coming. So once due to this pressure, consolidation happens. Consolidation happens. Okay. So when as the water follows Pascal's law, every point, what is Pascal's law? At every point, the pressure in every direction, any direction, at any point you take, the pressure in all directions is same. Okay. So due to this water, the sample will be subjected to the same pressure. All round pressure will be same in every direction. So when the pressure is same in every direction, soil will not fail. If anything is subjected to equal pressure, okay, all around, it will not fail. Especially soil will not fail. This will not fail due to confining pressure. Then what should you give? You have to give pressure in one direction at least. You have to apply extra or you have to loosen that pressure so that the pressure is different in one particular direction. Because of that, soil will get D shape. So when it will be in the D shape mode, then it has the opportunity to fail. That is the reason why you will apply another stress from here, that is called deviatoric stress. Deviatoric stress. So when you apply this, the vertical stress on this top will be different compared to the sides. Because of that difference, which is the deviatoric stress, difference is deviatoric. So because of the difference in stress, the soil will fail. Okay. So this is the concept in the triaxial test. This is the concept of triaxial test. What is unconfined compressive strength? Unconfined means there will not be any confining pressure. That's it. There will not be water. Okay. There will be only deviatoric stress directly. Okay. Let me take to this here and let me take to this here. Okay. So there will not be, you will be, so there will be acrylic cylinder as usual, but there will not be water. There will be only one rod. There is no water. The pressure is only applied vertically, okay, at the top surface. So the all round pressure generally denoted as sigma 3, that is 0 here. The vertical pressure is sigma 1 is nothing but sigma 3 plus sigma d, deviatoric stress. Here it is anyway 0, it will be equal to deviatoric stress in unconfined. Unconfined. Unconfined, what is this? Unconfined compressive strength. Okay. Now when you find out this d, which is nothing but sigma 1, okay, sigma 3, you can draw the Mohr circle, right? So what is sigma 3? Sigma 3 is 0. What is sigma 1? Sigma 1 is sigma d or something like this. Okay. Sigma 1, sigma 3. So by drawing a circle, taking these as ends of diameter. So, so here in unconfined compressive strength, we use only clay because sand will not stand like this without any support from the water. Water is nothing but support only. You are applying pressure. That means the soil is objected from falling. Suppose if you take sand, can you make a cylinder by using sand? It will fail. It will just fall. Whereas the clay has the automatic strength, that is cohesion. Because of that cohesion, you by using clay we make Lord Ganesh statues because it can stand on its own because of the cohesion. Can you use sand to make any Lord Ganesh statue? You cannot. That is so. This unconfined, without water you can use only clay. When you use only clay, the friction angle value will be 0. So when the friction angle value is 0, it should be 0. So that means, suppose, what is the more Coulomb failure envelope? It is something like this, where this is C and this angle is phi. If phi is 0, it should be horizontal. It should be horizontal, as well as it should touch the Mohr circle at one point. So that means you can draw only line which touches this peak. Okay, horizontal. It should be horizontal, properly horizontal. So this is C, we know. Okay, and what is Cu value is equal to now? What is sigma 1? Sigma 1 is nothing but sigma d. Sigma d is nothing but the vertical stress. Okay, this sigma d is nothing but called compressive strength, because you are using this as compressive, and at failure this sigma d is nothing but compressive strength it is called as. So that is what unconfined compressive strength is 54 kPa. Here it is given sigma d as 54 kPa. Now what is Cu? Can you tell me? So it is nothing but radius. Cu is nothing but radius, because this height is radius only, and this is diameter. This is 54 is diameter. So you to find out radius 54 by 2. Okay, this is nothing but this. This is also radius. This is also radius. This is 54 by 2. So finally, Cu will be Qu, or sigma d by 2. 54 by 2, 27 kPa. That's how Cu is 27 kPa in this question. Okay, in this question this is 27 kPa. Okay, now square footing. Let us, by using in the same clay, having the same properties, compressive strength and cohesion value, this, if you are going for this square footing 4 meter by 4 meter, and it is rested upon, this is which question? 55 question. Okay, 55. So what is it is rested upon ground level only, ground surface, 4 meter by 4 meter. This is 4 meter, and in another direction also it is 4 meter. On the surface above the clay, ultimate bearing capacity of the footing. See, ultimate bearing capacity of the footing formula, Qu is Cnc plus Qnq plus of gamma b n gamma, right? C is cohesion, Nc is the bearing capacity factor, which is equal to 5.7. Okay, for clays, only for clays I am saying. Okay, Q is nothing but the gamma, effective gamma, it may be gamma dash or gamma bulk, whatever, into df. Df is the depth of foundation. Suppose if it is from the ground surface to the bottom of the footing, this is df. Okay, this is df, and gamma into df will give you nq, and this is equal to 1 in case of clays. Okay, and gamma, again gamma b is nothing but the width of the footing, and n gamma is the factor which is equal to 0 for clays. So anywhere in this formula, can you see the length? Anywhere? Can you tell me, is there length or another direction, the dimension, lateral dimension of the foundation, is there any anywhere here? No. So then, if it is square footing, how does this formula know that it is square footing? So this formula is not for square or rectangular or circular. This is for strip footing. Strip footing, I told you in the few previous classes, maybe 4 or 5 classes ago, I have told this is strip footing. Strip footing means whose width is very much less compared to its length. Okay. So in that case, we'll go for 1 meter length. So roughly for 1 meter length, what is the strength? We don't go for full length. For each 1 meter length, what is the strength? In that case, no need to keep 1 meter because it is already multiplied. So if you want to multiply anywhere, okay. So this is only involved. B is only involved in this formula because B is the only dimension which will be given for the strip footing. Length will not be given. So to convert this formula to continuous footing, this is strip footing is nothing but continuous footing. Okay. To convert this formula into circular, square or rectangular, we need to use some additional factors. Okay, I'll tell you. So, so just to write for circular footing, you just have to keep 1.3 multiplied CNC. You please note down this. Okay, gamma d and q as usual, gamma d of nq plus here 0.3 will come instead of this is how much 0.5, zero point 0.3 will come in that place. That means how much should you multiply to get 0.3? Can you tell me? How do you get 3 by 10 is 0.3, right? So how much should you multiply to 1? 3 by 5? Yeah. So multiply 3 by 5. So it is very difficult to remember anyway. So that's why you just multiply in place of 0.5. 0.3 gamma b n gamma. Okay. See, b is here diameter because it is circular. So b is nothing but diameter. So now uh, we'll go for square footing. Again QU, again it is 1.3 CNC plus gamma D and Q. Okay, here in this case 0.4 gamma B and gamma, and B is nothing but width of the footing. And rectangle, for rectangle QU equal to 1 plus zero point 0.3 into B by L CNC plus gamma D and Q plus 1 minus zero point 0.2 B by L is the factor. For this you have to multiply total 0.5 gamma B n gamma. So these are the formulas. So if in rectangle footing B by L, two different, this is length, this is B. So if B and L are same, that is square, right? So put B equal to L, so you will get 1.3, fine. And if you put B by L 1.1 minus zero point 0.2 is 0.8. 0.8 into 0.5 will become 0.4. Okay. So just you can remember in that way. You can remember only this formula. Automatically you will get square, and circular is you have to remember. So now given question has circular footing and B is 4 meters. So now using this formula, I'll write that formula B equal to 4 meter. Okay. And what is DF value? Can you tell me what is the DF value? It is surface footing 0, because from the surface to the depth of the foundation it is df is 0. So df is 0. What are all the things we require? So nc for clays, remember this is 5.7, nq for clays is 1. Okay, so anyway q equal to 1.3 cnc plus uh, gamma df nq, and that is 0 anyway because n gamma is 0. So 1.3 c is how much? 27 we found out. Nc is 5.7. Gamma, let it be, df is 0 because df is 0, so nq is 1. What is the value? 1.3 into 27 into 5.7. Can you tell me? Can you tell me? So what is the nearest integer? 200. So can you tell me what is the answer? Answer is C. Okay, 200 kPa. So is there any doubt here? Yeah. So can we close the session? Yeah. So I'm closing the session. So we'll meet next Thursday.